So yesterday we talked very quickly about the different types of acid-base theories. Actually, that's yesterday's agenda. I didn't get a chance to change it. And it was very much review, right? What I need you to take from that is really the most important thing is that conjugate acid-base scenario where we have a Bronsted-Lowry acid donating a proton to a Bronsted-Lowry base in a Bronsted-Lowry acid-base reaction. And again, it's very much review. Today, also very much review. Like I said, and I said this yesterday, that in the grade 11 curriculum, it doesn't have, and it doesn't require us to go through as much detail as I do concerning pH and pOH and H3O plus concentration and OH minus concentration. But I feel that's a concept that you can easily understand at the grade 11 level, and it saves me a little bit of time at this level because it took me like 2 or 3 days to get that concept, you know, kind of in your mind so that you were confident with it. And now I can rush through this in 1 day, and you'll have it reviewed, and we can then move on and apply our knowledge of pH and pOH to acid-base equilibrium. That's really what we want to do. We want to get to the equilibrium discussion. So today we're going to talk about strong acids and strong bases, what makes them strong, all right? And then we're going to talk about, again, that autoionization of water. We're going to talk a little bit about that, you know, that silly game of keep away when it comes to that H+, that idea of an acid giving that H+ up. And then we will quickly review on how we can calculate these values because, again, when we're dealing with the equilibrium concept concerning acids and bases, we're going to need to be able to calculate pHs without worrying about it. Again, it's going to become again one of these tools. Like when I introduced you to molar mass, right? You probably took some effort and time the first time you used molar mass. Now, if you need a molar mass, you don't even think twice about it. I need you to be able to do the same with pH and pOH and H3O plus and OH. I need it to just be a tool that you use at the end of a question. All right. So let's define a couple of things here, strong acids and strong bases. And then I've got a bunch of slides that talk about pH and pOH, but I'm not going to use the slides. I'm going to just do a little summary on a little pH chart, just like we did last year. We're going to quickly get to our equations and then our practice problems. And the textbook goes into great detail. It has lots of practice problems on this. Whereas the grade 11 textbook doesn't, because really it's part of this curriculum. So what I want to do is I want to get to that homework and give you lots of time to just practice over and over again calculation of pH and pOH. Last year we talked about strong acids and strong bases, and we say that it completely ionizes. And to us studying an equilibrium, that's not very exciting. That's a reaction that goes to completion. What we want to get to is the weak acids and the weak bases. They're the ones that have an equilibrium constant that isn't too big and too small, and gives us some interesting information. So today we're just going through the strong ones, the easy ones. Strong acids have a weak attraction for their H+. It means they want to give that H+ up. If we, again, like the analogy I used last year, and it's not a bad analogy, if a strong acid were, you know, playing a game of keep away, it would be great at it. It would get rid of it. If it were to be given the H+ back, it would get rid of it again very quickly. So that if we took a little snapshot of all of the H's and negative ions, for a strong acid, all the H's would be off and attached to a water to form an H3O+. So there's lots of H3O+ in a strong acid. So here's our Bronsted-Lowry example. Technically, it's not exactly 100. It's approximately 100. And because we already know about equilibrium, I could actually put in the proper equilibrium arrow because it is. And in this case, the arrow that goes to the products would be really big, and the arrow that goes to the reactants would be really small. And I'm going to be giving you a chart that has the K values for all of these different acids, whether it's weak or strong. Because these are all equilibrium. That's where we want to get to. We want to get to talking about this as an equilibrium.
Excuse me, Mr. Peter, can I get that Charlie Stevens in the office for a moment?
Yep. And in this case, if you have a, well, not in this case, but if you have a strong acid, the K is big. Now, when I say big, it's not like 10 to the 52. We're going to have slightly different ideas on what big, medium, and small are in terms of acid-base equilibrium than compared to a regular equilibrium. I think for this one, I think it's something like 10 to the 1 or 10 to the 2. It's like 100 or 10. That's big in terms of an acid. In terms of an acid, super weak is like 10 to the minus 14, and medium in the middle is like 10 to the minus 7. And those numbers do come from our concept of pH. So we're going to be learning a little later on that the size of the K is kind of linked to the pH as well. So the attraction of the Cl for the H plus is very weak than the attraction for the water and the H plus. So we get a transfer. Again, the Cl is better at the game of keep away. And so in this reaction, we have all kinds of ions, it's a strong electrolyte, and very few molecules. Now, there's lots of water around as well. It's not that I'm saying that all the water's been turned into H3O+. It's just that every single HCl that's been put in that water will transfer its H over. So there's still lots of water molecules kicking around. It's just some H3O+ has been formed. Now, let me just look ahead here. Yeah, I do want this list. I do want this put down. In a moment, I'm going to deviate from the PowerPoint slides and go to the Smart Notebook and just kind of create the notes and the equations, because I think there's something like 5 slides worth of information. I can do it easily on one. So strong acids include the hydrohalic acids, right? Like hydrochloric and hydrobromic and hydroiodic. Hydrofluoric is not strong. There's a large electronegativity difference between that H and the F. That makes this almost ionic. It makes the H stick tight to that F. It does not lose its H's as readily. So this is actually weak. We will be using HF in many examples because it's a good classic weak acid. Now this second part's important as well. The oxyacid in which the number of O's exceeds the number of ionizable H's by 2 or more. What a great statement that is. That's your classic kind of quantitative statement that we really have to think through and look at our examples in order to make sense of it. I am going to expect you to know this, but like I said, in another day or two, I'm going to give you a chart that has the constants for these equilibrium reactions, and many of these are on there, and you'll notice that their K is big. So I'm telling you, I need you to memorize which acids are strong, but in the end, when I give you that table, you'll actually be able to see which ones are strong by looking at the what we call acid constant. right? The K for this equilibrium. The number of O's exceeds the number of ionizable hydrogens by 2 or more. So if we take a look here, right, at the H2SO4, there are 2 H's and 4 O's. The number of O's is greater than the number of H's by 2 or more. So 2 and 4, yes, there's 2 more O's than H's. HCO3, 1 to 3, are there 2 more O's? Yes. All right? 1 to 3, 2 more O's? Yes. All right? If I had something like, instead of chloric acid, if I had HClO2, which is chlorous acid, 1 H and 2 O's, the number of O's don't exceed the number of H's by 2 or more. That is not a strong acid. That's a weak acid. It has to do with the ability of oxygen to suck electrons toward it. Oxygen is highly electronegative, and it will draw the electrons towards it and kind of make that H fall off with ease. All right? So it's kind of sucking the electrons away from the H, making that covalent bond a little weaker, and so when it gets into the water, that H is able to fall off. All right? That's the reasoning behind it. Let's define the strong bases, and then we will get into our discussion on pH and all that other good stuff. So again, this is kind of like a review from last year. We're really only talking about the metal hydroxides, and then ammonium hydroxide is also included in there. Now we know also about solubility. Last year I would have just said ionic hydroxides. The OHs fall off, you got hydroxide in the water, you've got a basic situation. But now we know that there is a measurement of the ability to dissolve. And so the ones that are strong are the soluble ones. Again, sodium, potassium, in this case barium is also highly soluble. Those will fall off with the greatest of ease. Their KSP is large. I don't know, we don't have a table of well, we do have a table of KSPs, but I don't put anything, or in the textbook, there isn't any sodium hydroxide or potassium hydroxide or barium hydroxide, because they're very soluble. We just simply say they all fall apart. Their ability to fall apart in the solution is great. We just looked at, and you just got your lab back, for calcium hydroxide, right? What did we say the KSP was? I think there was like 5.5 times 10 to the, was it minus 5? Or was it minus 6? Was it minus 6? It really doesn't matter. Minus 6. Whether we've got it absolutely correct or not. But notice for this is a small K, which means most of it stays, we'll balance it up properly. Most of it stays as a solid, right? So when you put the calcium hydroxide in there, a very little bit of it dissolves. This is not strong, right? This is weak. This would be weakly basic, all right, because of the small K. So again, I'm just putting that as an example of what isn't strong, I guess, for our video people. Magnesium hydroxide is the same way. If we were to take a look at the magnesium hydroxide KSP, it would be small. Okay? Now that doesn't mean it can't neutralize something. If you were to put an acid with that calcium hydroxide, it would actually start to dissolve the solid calcium hydroxide, and it would still be able to neutralize it in the end, but it wouldn't be basic on its own. Wouldn't be very basic on its own. That's the same with magnesium hydroxide. Magnesium hydroxide doesn't dissolve very well. Its KSP is small. If you have an upset stomach, you take milk of magnesia, which is essentially a solution of magnesium hydroxide that has some solid in it. You give it a shake. It looks cloudy. You drink it down. It ends up in your stomach with all kinds of hydrochloric acid from your upset stomach, and it eventually dissolves and neutralizes that acid. The reason you wouldn't do that with sodium hydroxide is because if you dissolve sodium hydroxide in water, it would already be ionized as hydroxides, and as you drank it down, those hydroxides would react with your esophagus, and it would be highly unpleasant. You would have you'd have great burns, and you would die. It would be a good thing. But the milk of magnesia, the magnesium hydroxide, you could probably do it with calcium hydroxide. As you drink it down, very little of it has actually produced OHs, so it's not highly basic to your esophagus as you swallow it, but then once it's in your stomach, there will be a breakdown of those ions, and it'll neutralize it in that place. That's why you can take magnesium hydroxide for an upset stomach, but you don't want to take sodium hydroxide for an upset stomach, because it's strong. Okay. You can write that one down, and then I'm going to... Then am I going to switch, or have I got one more? Freeze. Nope. Then I'm going to switch to the other thing there. So I introduced you last year to the autoionization of water. At one point I would have said, water doesn't dissolve in itself. That's absolutely insane. And then I would have whispered and said, that's a lie. And then I would have got to this point in the course and I would have said, you know what, water does kind of dissolve in itself. One water molecule can react with another water molecule, can transfer that proton and produce a hydronium ion and a hydroxide ion. And I probably described it as if there's a game going on even in pure water. So let's say you had pure water and there was no acid, no base in there. It's like the water molecules kind of decide, well, this is kind of boring. No one's here to play the game. We'll play it by ourselves. One water molecule bumps into another water molecule, transfers the H. If it's a game of keep away, excellent. The OH is winning. If it's a game of capture the flag or something silly like that, flag football, excellent. The H3O is winning. Got the H+. However you want to think about it, it makes no difference. And this goes on continuously. It's an equilibrium. It's a dynamic equilibrium. One of those H3O pluses can bump back into one of those OHs, transfer it back, turn it back into water. A couple of other water molecules can bump into each other, transfer it over, turn it back into H3O plus and OH minus. It goes on continuously. And this happens in any aqueous solution. And just like any other equilibrium, we can write an equilibrium expression for it. Liquids don't count. We don't count them because they're pure. Actually, we calculated the molarity for pure liquid. It was something like 56. So we only have the products, H3O plus times OH. And that's true for any aqueous solution that has water molecules in it. That equilibrium system will be intact. All right? Now let me switch over to Smart Notebook here and change things a little bit. No, we want to switch to this. And, oh, you can't see because I froze. That. And this, again, is going to just be my pH. I want to talk about the pH scale in this case. And I think I want the black pen today. The pH scale. And again, I'm visual. I would rather take a note in a bunch of pictures than a whole bunch of words. And my next slides are a whole bunch of words. And I just want to express it with some pictures on it. And just like I told you last year, 0, 7, 14. And let's break it up and put some lines in there. And I said, don't worry so much about it. And I said, for those of you who are very picky about it, you're going to get your rulers out. You're going to have 14 centimeters. And you're going to put a mark at every centimeter. That's great. That fits nicely on the page. I'm not that picky, so I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And because I've been doing this for many years, it works out quite nicely. And we already know that 7 is neutral. I don't think we need to write that. Well, I guess we could here. Neutral, this is what we would say is basic, and this is acidic. And when it's neutral, we learned about this last year, that the concentration of the H3O plus is equal to the concentration of the OH minus. And we might also remember that that concentration is also equal to 10 to the negative 7, because remember, pH is the power, the exponent, right, of the concentration of H3O plus. Okay? Now this gives us a special little clue. It means when it's neutral, Kw equals H3O plus times OH minus, and when it's neutral, that's going to be 1 times 10 to the minus 7 times 1 times 10 to the minus 7. It's actually 1.0. We do know it to 2 significant digits. And I think we can multiply that in our heads. We're adding the exponents, right? That means the Kw is 1.0 times 10 to the minus. Oh, it's a Wednesday pause. 14. And that is the Kw at 25 degrees Celsius. That's an important number. We're going to be using that. And that's where our pH scale of 14 comes from. It comes from that Kw value. It comes from the fact that we have the equal concentration, and that's what gives us our 14 value out there. Okay? So if I'm down here at acidic, let's say that we added some HCl. And what that does is it gives me a large amount of H3O plus. Remember that? It gives us lots of H3O plus in the water. Okay? Now this statement here, this Kw is, and I really want to stress this, this is true for all aqueous solutions. What that means is this constant here, the Kw, is true whether I have neutral, acidic, or basic. So what that means is, as I move down here so that my H3O plus gets bigger, if the H3O plus gets bigger in this equation and the Kw is constant, what must happen to the OH minus number? It's got to get smaller. All right? So in terms of an equilibrium calculation, when we add H pluses and we make lots of H3O plus and the H3O plus goes down, the OH minus must, or sorry, the H3O plus goes up, the OH minus must come down to keep that constant. So it's much greater than the little amount of OH minus. It's like we've made the game unfair. In an acidic situation, you have actually 2 games going on. You've got the game with the HCl. All right, the HCl, they're like the professionals. The professionals are coming in, they're going to dump off all those H pluses, and the H3O plus is going to go up. Then you've got the game within the water. It's as if the water, game that was going on that had this nice balance between the H3O plus and the OH. It's like it became unfair, and a bunch of H3O plus competitors came in. That means the OH guys didn't have a chance. They're going to be transferring H pluses to the OH, turning them into water, and that concentration is going to go way down because they're going to be transferring their things over. All right. Over here at basic, if I add some NaOH, the opposite scenario is true. It's like I've brought in the professionals. We've loaded the solution with OHs. Now the H3O plus guys don't have a prayer, and I'm going to have lots of OH minus, and that's going to be greater than the little amount of H3O plus that's going to be in there. Does that sound familiar to everybody? Okay, so you add lots of base, and your H3O plus has to go down. And it's all governed by this equation right here. Okay, let's put down some of our good old equations, and then we'll do some example problems. So we know that what am I doing here? Got to get my pen back. pH equals negative log H3O plus concentration. If I want the H3O plus concentration back, that's equal 10 to the exponent negative pH. You guys probably even reviewed this for the grade 11 test, which is fabulous. We know that pOH is the negative log of the OH minus concentration. And we know that OH minus, if I want to get that back, it's 10 to the negative pOH. Let me know if anything is earth-shattering here. I don't believe it is. If I want to jump between pH and pOH, because if I'm given a question about bases, I'll have the pOH and I'll eventually want to get to the pH. There's actually two ways in which we can do this. I can actually use this guy. Kw is equal to concentration of H3O plus times the concentration of OH minus, and that Kw is equal to 1 times 10 to the minus 14. I don't introduce that one to you in grade 11 because I have to tell you what a Kw is in order to do that, and you guys have no concept of what equilibrium is at that point, so it really has no meaning. I don't even like using this because if I take the negative log of this entire thing, and I've got a 14 in there, then I have the version that we're used to. 14 is equal to pH plus pOH. And these two equations are really the same, except it's really taking the negative log of this entire expression that turns it into that. I'm not going to worry about the mathematics of it at this point. But if I take the negative log of the K, it's going to be 14. And if I take the negative log of these concentrations, I'm going to get the pH and the pOH. And when you're dealing with logs and they multiply, you can add them up. It's something like it's that goofy log rule, but I'm not going to get into that right now. So like when we did the log rule and you have a multiplication, you can do some goofy stuff. We're not going to worry about that. Okay, so there's our equations at this point. There was one other thing I wanted to add to that, and I cannot remember what it is, so it's not a big deal. I was going to say something, but it cannot be that important. If we come across it in our examples, we'll gather it up. PowerPoint slide. So there's all that stuff that I just wrote. Blah, 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 blah. That's excellent. That's good. There's our pH one. Look at, there's some practice of taking negative logs. That's fun. Oh, and that's going the other way. That's beautiful. I just did that example calculation. You can even just put examples. E.g., pH, pOH calculations involving strong acids, strong bases, however you want to write that down. Again, I don't know if you want to write down A. I'll do A and B both on this slide. I can easily put it in there. You might already know how to do this. This is excellent if you do. The because they're strong, we're assuming it's 100% ionized or 100% dissociated. If it's weak, we've got to use an ice table or something to figure out how much OH there is. We'll do that tomorrow. And actually, there's lots of shortcuts. Sometimes shortcuts are not so good because we take the shortcut when we're not supposed to take the shortcut. We all kind of fell into that trap. So I'm going to show you lots of shortcuts when we do the weak ones, but we've got to be aware on when we can use those. In these cases, 100% ionized. So in A, assume 100%. It's ionized 100%. Which means if I have 0.057 moles per liter of HBr, and I got to be very careful because it's only one H that falls off. I'm going to do an example of this. And there's one H for each HCl. I got to be very careful with this. This is going to fall to pieces right here. Plus one, and one HCl. What's that? It's HBr. I'll tell you why I've got to be careful with this. I'm going to make up another example here in a moment, and I'll explain why we've got to be careful with this. And we've got to be careful with it with acids. It means I'm going to have 0.05, I'm all messed up now because I'm worried about what I've done here, 7 moles per liter, and that is H+, right? H+. There's my H+ ion concentration. Which means pH is going to be the negative log of 0.057. Again, we can always check that. -1, -2. We're in the -1, -2 range here, which means we get rid of that negative, so we should have a pH in the 1 to 2 range. And what do we got? What do we got, Shauna? 1.24? 1.24. And let's always round our pHs to 2 significant digits, all right? The rules for logs and significant digits are not the same as straight up multiplication rules. So let's just always express our pH in terms of 2 decimals, okay? All right? Always express pH in terms of 2 decimals, whether it's 14 point something something or 1.24, always 2 decimals if we could. Let's do the BaOH2, and then I'll tell you why I wanted to be, I was a little leery about this maneuver right here. I'll show you in one more example. So I'm going to clear this. What's happened? No, oh, we got to calculate all that other stuff, don't we? Darn. Can I get it back? Nope, I can't. That's okay. We will keep going. I'm worried about this little scenario that I've just generated. Okay, let's just keep going on this. What did we find that the pH was? pH is 1.24. And we know that the H3O plus is, what was it? 0.057, right? Moles per liter. And what I want to do is I want to find the pOH and the pH. Because what we have to do in many cases, especially if we're given OH, we've got to calculate it all. Now, what I want to stress to you is do this all in one shot. You should be able to do H3O plus, pH to pOH to OH without clearing your calculator. Has everybody cleared their calculator at this point? If you've cleared your calculator, here's what I want you to do. If you've cleared it, put in your negative log of 0.057, right? Negative log 0.057 equals, and you should get 1.24, right? You've got that on there. So the next move you do is go pOH is equal to, and then it's 14 minus pH. 14 minus pH. It's good to write it down, but you really don't have to, because what you're going to do is you're going to go 14 minus answer equals. Everybody got the answer key on their button? If they don't, you've got to do a little addition of some numbers there. So you do negative log 0.57, and then you get 1.24, you write it down. Then you right away go 14 minus answer equals, and you've got the pOH. What's the number there? 12.76. And then to get your OH value, you're going to just do 10 to the negative 12.76. You're just going to go 10 to the negative, to the exponent, and then answer, negative answer equals. And it'll spit out that number. Okay? (1.74 times 10 to the negative 13? 13 moles per liter. And it's the same if you're starting with the OH, it's just you're moving your way to the pH. But you should be able to do that, boom, 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 quite quickly, because we're going to be working back and forth with both of them. All right? Let's clear this again, and we will now do the OH example. Does everybody have those numbers down? Everybody got that down? Oops, back up. Yes? You got it? Okay, so I'm going to clear this. Let's now deal with this guy. Barium hydroxide, highly soluble. (0.0050 moles per liter. And you know what? You don't have to write this all down. I'm doing this to get it into everybody's notes, but how much OH is there going to be if it's BaOH2? How much OH? Yep. 0.01. We're multiplying it by 2. All right. And again, I'm just doing this kind of officially. 2 OHs for each one. BaOH2, 0.010. Again, it's the two significant digits, moles per liter of OH minus, right? So we actually have the OH minus right there. OH minus is equal to 0.010 moles per liter. All right? You don't have to show me that step if it's obvious. Now we can go straight to pOH. I really don't even need to see it written down unless you make a mistake. If you make a mistake, then I'm on a test. I don't have anything to give you. If you write down negative log of 0.010, then you make a mistake, I can give you something. But like I said, you've got that number in your calculator, negative log answer equals, what do we got? Yep. 2. We'll put 2.00. It is 2, you're right. And now to get the pH, sorry, what did I just write there? pOH in square brackets. I'm still worried about this little thing I got to tell you. Now to get the pH, all you got to do is 14 minus pOH, or 14 minus answer equals, this one's easy, 12, right? 12.00, I want 2 decimals on those. And then to get the H3O plus, again, I don't need to see it, but if you make a mistake, you're running the risk. (10 to the negative 12), well, if you run that in your calculator, you're going to get 1.0 times 10 to the negative 12 moles per liter. So what I'm trying to get across to you is that using your calculator, you're able to fly right through those for quick calculations, okay? Now here's what I was kind of tripping over. I used the mole ratio in order to determine the concentration of the H pluses. Let me clear the ink. But if I had a third example, right, and I had something that was strong like 0.025 moles per liter, and it was H2SO4, all right, when it comes to acids, we only take one H off at a time. You only remove one H, all right? And this is not as easy of a question. Don't even write it down. Don't write it down. This is not as easy of a question as it looks. Because what happens is you get 0.025 moles per liter of H pluses, but then the HSO4 minus, all right, it might also lose some H's, but it's a weak acid. Losing the first one is strong, but the second one could be weak. So we could have just a few of them fall off. And so when you've got an acid that has more than 2 H's on it, you've got to take the H's off one at a time, and this is more complex. This is a higher complexity problem that we're not going to deal with in this course, but you would deal with in university. So I won't be giving you any of these that have more than 2 H's, and that's because the 2 H's don't just fall off in water, right? It's a tricky situation. So I'll only be giving you ones in the strong ones that have 1 H. Okay, so let's clear that ink. Let's do a couple more examples here. Here's example number 2. This is actually the last example. This just kind of gives you the heads up on how the textbook's going to give it to you. This is not complicated at all. We're given grams. We're given some water. We need to convert the grams to moles. We need to find a concentration of the barium hydroxide. Then we do exactly what we did in the last example. So again, this is super review. What am I going to need to convert my grams to moles for barium hydroxide? Oh yeah, molar mass. We don't get opportunity to use that much these days. It's nice when we can hear you guys chant that. So I'm going to need barium hydroxide. 2 times 1, 2 times 16. I don't know what barium is. We haven't used our periodic table that much these days. Barium. 137.3. 137.3. And I don't have the 0.0 on here, but we know that. We know it's 0.0. We'll take it when you get it. 171.3. 171.3 grams per mole. .50 grams. 171.3 grams. Yep. 0.0. Did you say 146? 146? 146 moles. We've been using concentration so much, all you have to do is write, you can write down C equals N over V if you'd like, just for good times, right? But in the end, I need moles per liter, so 0.0146 moles divided by 0.100 liters, which is C equals N over V. But again, all you got to do is turn it into the unit you need. We want moles per liter. We need a concentration, 0.146 moles per liter. Now that's the concentration of barium hydroxide. So what's the concentration of hydroxide? If the barium hydroxide is 0.146, what's the concentration of just the hydroxide? Yeah, Christian? We doubled it, right? 0.292 moles per liter. And now you're just using your calculator. You're off to the races. You're going to get a pOH. You're going to subtract 14 from that to get a pH. You're then going to run that through 10 to the negative whatever to get an H plus. And at this point, I'm not even going to write the equations down. Just tell me some of these numbers when you get them. Well, you can tell me them all because you're going to just calculate, do them all. Negative log, if you've got that in your calculator, answer equals 14 minus answer equals 10 to the exponent negative answer equals. That answer button is a fabulous thing. So we'll take all three when you get them, and I'll take the pHs and pOHs to 2 decimals. That's what we'll go with on this. If you're not sure how to make your calculator do this stuff, I'll be offering up some calculator training in a moment as you work on the problems. Yesterday for the grade 11s, we got into mole calculations. We needed to use Avogadro's number. I had to show them how to put it into scientific notation. You were all there once. I did training for you guys. It's a good time. Here we have pOH. Who's got it? Christian. 0.53. That's good enough. Two decimals is good. 0.53. Yeah, I think that's in the right ballpark. It's quite strong, right? And pH? Keep going, Christian. Just read them off. He's not ready, man. You should have been able to fly through that. Who's got it? What do you got? Shauna? 13.47. And? Times 10 to the negative, 14? 14? Times 10 to the negative 14? It's got to be. It's close to 14. 14 moles per liter. All right? OH is big. And for acids and bases, big is 1. 1 is like huge. H3O plus is really small. We can fly right through those very quickly and easily in order to get all 3 or all 4. Okay, and the textbook has plenty of them. Plenty of them. All kinds of them. Takes you 2 seconds to run through some of these. Some of these, they give you just an H3O plus concentration. You plow through it, right?